Welcome to The Explainer. Our whole goal here is to take these really complex topics and, break them down into something clear and straightforward.
If you're an RF tech or an engineer, this quote from Analog Devices probably hits pretty close to home. Impedance matching. Yeah, it's one of those fundamental, and let's be honest, sometimes nightmarish parts of the job.
Now, this is actually part 10 of a big 20-part series we're doing, and it's all based on a super detailed report by the RFI detectives. And today, we are diving headfirst into the core issues of impedance mismatch and all the interference it can cause.
All right, let's get right into it. First things first, we need to clearly define the problem. What exactly is an impedance mismatch?
Well, to put it simply, a mismatch happens when the impedance of your antenna, or what we call the load, doesn't line up with the impedance of the transmission line it's connected to. It's like the power source and the antenna are trying to have a conversation, but they're speaking completely different electrical languages. And this creates what we call an impedance discontinuity. I want you to picture a wide, smooth-flowing river. That's your RF energy. Now imagine that river suddenly slams into a dam. Not all the water can get through, right? That dam is your impedance mismatch. It's a barrier. So you might be asking, what happens to all that energy that can't get through? Well, it doesn't just vanish. It actually gets reflected, bouncing back down the line, creating what you can basically think of as echoes. And we have a way to measure this. It's called the reflection coefficient. Think of it as a scorecard for your connection. It's just a ratio of how much power is bouncing back compared to how much you sent out in the first place. On this scorecard, a 0 is perfect, a flawless match. A 1? That means all your power is coming right back at you. Now, these echoes, these reflected waves, they travel back down the line and start crashing into the original signal that's still trying to move forward. And this interference creates this weird pattern of high and low voltage spots along the cable. We call these standing waves. And that pattern of standing waves brings us directly to our next huge metric, VSWR, or voltage standing wave ratio. VSWR is just how we measure how bad those standing waves are. It's a simple ratio. You take the highest voltage point and divide it by the lowest voltage point. That's it. So in a perfect system, a lab fantasy, there's no reflection, the voltage is totally constant, and your VSW is a beautiful one-to-one. But out here in the real world, any mismatch is going to give you a higher ratio, and that number is a direct signal that you're losing efficiency and power. Okay, so we have reflections causing standing waves, which we measure with VSW, but so what? Why does this actually matter? What are the real, tangible consequences of a high VSW? Oh, it matters. The consequences are pretty significant, actually. Those reflected waves cause destructive interference, which just messes up your signal. You get a direct loss of energy that we call mismatch loss. And if you're working with high-power systems, all that reflected energy can actually travel back and physically damage your transmitter. Let's just focus on mismatch loss for a second. This is real, measurable power in dB that gets reflected away from your antenna and never gets out into the world. It's energy you're paying for that's just completely wasted. It's a direct hit to your system's performance. So clearly, we can't just let this happen. We have to fix these mismatches. And thankfully, engineers have a pretty well-stocked toolkit for taming this exact problem. The main tools in the kit are called matching networks. You can think of them as little filter circuits, like pi or T filters, and their whole job is to cancel out the mismatch. They basically trick the transmission line into thinking it's connected to a load with the perfect impedance. And this slide shows two classic ways to do just that. On the left, we've got shunt matching, where you add components in parallel to the line. And on the right, you see a quarter-wave transformer, which cleverly uses a specific length of a different transmission line to act as a matchmaker. Both are really fundamental techniques for building these networks. But, doing all the complex math for these circuits can be a real headache. So, is there a more intuitive, maybe a more graphical way to solve these impedance problems? The answer is a big, resounding yes. Enter the Smith chart. If you're an RF, you know this thing. It's this essential graphical map that puts the entire world of complex impedance onto a single page. It lets you plot your bad match as a point and then visually trace a path, adding components along the way right back to the dead center of the chart, which is your perfect match. And all of this brings us to our final and I think most important point about why mastering this stuff really, really matters in the real world.
I want you to really think about this quote, which we've adapted from the RFI Detectives report. Proper impedance matching is a zero-cost performance optimization. Let that sink in. Instead of going out and buying a bigger, more expensive amplifier, you can often get way better performance just by optimizing the system you already have. It's about getting the most out of your gear.
Which leaves us with a final thought to chew on. As our wireless systems get more and more complex and the frequencies we use get higher and higher, how are we going to keep managing this fundamental challenge? Mastering these principles isn't just about being a good engineer anymore. It's absolutely critical for the entire future of wireless tech.